Hi everyone, welcome back. So this is our third class in the IE 515 Stochastic Process Modeling. So how's your semester so far? Is it good? I believe we do have like a little slow start in this class, but this class and then probably one or two more classes, we're gonna devote a little more time on the stochastic process, especially focusing on the Bernoulli process and Poisson process. Okay, and I will try to bring a lot of example problems. Okay, and then after that, we're gonna move to a new topic, which is Markov chain later, sometime very soon. Okay, so this is the handout for today. So basically, after we've done this, I'm gonna let you go. Okay. So before I solve the problem using the smartboard in front of me, let me give you a couple of minutes. Why don't you guys read through the problem description and then try to answer some of those if you could. Okay? So like I mentioned here, please be sure to state what probability distribution you assume for each questions. Okay? And of course, you can find the necessary probabilities in the tables, or you can compute them manually with a calculator, with a computer software. For example, Excel can do that, most of those computations. So anyhow, let me give you a couple of minutes. So why don't you guys make a pair, two or three people together, and then share your idea. So our class is pretty small in terms of number of students at the moment. So I want to take the great opportunity to know each other, okay? And then share your idea and work together. Oh, can I just follow this?
Sure.
And then just let you know, be sure to you come back this diagram. I believe this diagram is very useful that we talked about. At least it can show you how to distinguish Bernoulli process from Poisson process, or vice versa, right? And then I try to arrange the three different distributions belongs to Bernoulli process, and another three distribution belongs to Poisson process. Okay, and then I try to make that order. Okay, corresponds to number of events, time until the first event, time until the case event. Okay, so I believe this diagram is very useful for you guys. Even beyond this class, this can be very useful.
Do we know that it's going to be 1 in at n trials. We have a fixed number, which is the n trials, and we know that it's going to be 1. Or we can also say like 3, right? 1 divided 3, multiple 10, becomes frequency equals 7. This is for sure if we take like this. But, I mean, we want to make it complicated.
Okay, so for the first part, which distribution did you use?
Poisson.
Okay. Binomial. And you said?
Poisson because of the average.
Poisson?
But I would see time.
Okay, let's see. So let's work on that. So let me first read the problem description. We are working on the part 1. The foreman of a casting section in a certain factory finds that on the average, 1 in every 3 castings that are made is defective. Okay, so by reading through the problem description so far, you should be able to get the information about the probability of being defective, which is 1/3, right? So here, what did I do? Okay. Sorry, I pressed the wrong buttons. Okay, so here, sorry. Sorry, okay. Okay, here, every 3 castings, I'm going to use different. So we know that that's going to be 1/3, right? So we know that 1 in 3 castings are defective. And the question is, if the section makes 10 castings a day, what is the probability that one of these will be defective? So, of course, we are assuming that the defects are independent and identically distributed. Okay, that is our assumption. So, intuitively, what distribution we want to use? You remember? Yeah. Looks like binomial. Because last time.
Is it because of defective or not defective? That's why it's called binomial, or?
Defective, not defective. So first of all, is about something about the probability, right? Yeah. And last time we considered a single trial, Bernoulli trial, whose outcome can be either success with the probability P or failure with the probability 1 minus P, right? So Bernoulli trial has always ended up with 2 different results, either success or failure, okay? And we considered this binomial trial, and then if we make this single binomial trial independently, like n times, then I mentioned that binomial random variable counts random number of successes within those n different trials, okay? So this is it, right? We want to know that 1 out of 10 castings would be defective, right? In that case, we want to know, only 1 case will be successful within the 10 trials, right? So this is something about the binomial. random variable, right? So first of all, we're going to define the random variable. Let's say n sub 10. That is the number of defects in the 10 casting of here, right? In 10 casting, right? And then we can build up the desired probability using this random variable we just defined. So what is the desired probability? N sub 10 is what? It's equal to 1, right? So in that case, of course, n sub 10, this random variable follows binomial distribution with parameter n equals 10, p equals 1 over 3, right? So that's going to be 10 combination 1, 1/3 to the power 1, right? 1 minus 1/3, 10 minus 1. Is that right? By the way, you guys know how to compute this, right? 10 combination 1. How did you get this? Just I want you to record your memory. That's going to be 10 factorial over 10 minus 1 factorial times 1 factorial. Is that right? So what is that? 10 factorial. That's going to be 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. Over 10 minus 1 is 9 factorial. So it's 9, 8, 7, 6, 5, 4, 3, 2, 1. Times 1 factorial is 1, right? So all of these parts can be removed. So what is left over? 10. Okay? So 10 times 1/3 times 2/3 to the 9th power. That's going to be our solution. Does anybody have a calculator with you?
2.2.
You have 2.2 as the answer?
0.08.
0.08? 67? Okay. Yeah. In my previous calculation, I also have 0.0867. So it looks like you have the same answer. But I want everybody double check your computation. Okay? Okay, so let's move on to the next question. Okay, now if the section makes 10 castings a day, what is the probability that 7 or more defective castings are obtained? So it looks like we can still use the same random variable that we defined earlier, right? Then what is the desired probability? N sub 10 is what? We want to know the probability that 7 or more defective castings are obtained. So it's got to be greater than equal to 7. Is that right? So what is this? Probability n sub 10 equal to 7 plus probability n sub 10 equal to 8 plus n sub 10 equal to 9 and then n sub 10 equal to 10. Okay? Of course, this is same as 10 combination 7, 1/3 to power 7 2/3 to power 10 minus 7 plus 10 combination 8, 1 over 3, 8, 2/3, it's going to be 2, 10 combination 9, 1/3, 9, 2/3, 1, and then 10 combination 10, 1/3, this time 10, 2/3, this time 0. Okay? Yes?
Can you also do this the other way around, where you do the, instead of doing all that calculation, you could do 3, where the 3 that's not included here.
I'm sorry, but
So
could
you
you...
have 7 or more, right?
Right.
To 10.
Mm-hmm. The other way around
Yeah.
will be a little more work,
Oh, yeah.
right? This is better. So what you want to do is 1 minus probability n sub 10 is
Yeah.
less than, is that 7, right? Something like this. That's what you want to do, right? Yeah, sometimes maybe if you do this, then it'll be more, yeah, less computation, but in this case, this would be better, okay? Yeah.
What is the 2 divided 3?
Which one?
The 1 minus.
Because there is 1 minus 1/3. That's going to be 2/3, okay? So this part is actually 1 minus 1/3. Okay. So in my previous computation, I got 0.0196. Any of you got the same answer? Any questions so far? Yes. Oh, you want to write down? Okay. Is okay? Okay, so let's move on to the next question. Question C, if the section makes 10 castings a day, what is the probability that 1 or less defective castings are obtained? Well, this question is also very similar to the previous one, right? Using the same random variable we defined earlier, which is n sub 10. Less than equal to 1, right? So that's going to be probability n sub 10 equal to 1. Oh, I'm sorry. Yeah, it's going to be equal to probability n sub 10 equal to 0. Okay? So 10 combination 1, 1/3, 1 minus 1/3, 10 minus 1 plus 10 combination 0, 1/3, 0, 1 minus 1/3, 10 minus 0, right? So that's going to be 0.104, my previous computation. So that is same as 10.4%. Okay? Okay, so any questions so far? Okay, no? Okay, so we are good to go. So this is part 2. So in part 2, we are considering a game of craps. So in preparation for a game of craps, Nathan has asked you the following questions. The first question is, what is the probability of throwing a 7 or 10 at least twice in 6 tosses of a pair of dice? So we know that there are 36 different outcomes if you toss a pair of dice, right? 6 minus 6 is 36. Then out of those 36 outcomes, how many different ways you can obtain the outcome of 7 or 10? We need to have that number first, right? So how many different ways to throw a 7? So 1, okay, let me see. 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2. This is 3. And then 6 and 1. So there are 6 different ways to get 7. Is that right? How about 10? How did you get 10? 4, 6, 5, and 5. And then 6, 4. So there are 3 different ways. Is that right? So 1, 2, 3. Oh, this is not 7. Okay. Yeah, there are 6 different ways to get 7. But there are 3 different ways to get 10, right? So in total, there are 9 different ways to throw a 7 or 10. Is that correct? So there are 9 different ways. So let me just write down. There are 9 different ways of of throwing a 7 or 10 in a toss of the dice, right? So that's going to be, so we get the probability of throwing a 7 or 10. That's going to be 9 over 36, which is 1/4. Okay? There are 25% of chances that you are going to get 7 or 10 by throwing a pair of dice. Okay? So how do you define the random variable in this case? The desired probability is throwing a 7 or 10 at least twice. In how many tosses? 6 tosses of the pair of dice, right? So I would define n sub 6. Okay? What is that? That is the number of 7s or 10s obtained in 6 throws of a standard pair of dice. Does that make sense? Okay? So let me just write it down. That is the number of 7 and 10, 7s and 10s obtained in 6 throws of a standard pair of dice. Okay? So we are going to use this random variable to get this desired probability. Okay? So what is the desired probability then? N sub 6 is what? So we want to know the probability at least twice. At least twice. So it should be greater than, right? Greater than, equal to 2. Does that make sense? Okay? Okay.
So 2, 3, 4, 5.
Yeah. So in that case, earlier Mahmoud suggested, right? We're going to go other way. That would be better. N sub 6 is less than 2. Okay? So that's going to be 1 minus probability N sub 6 equal to 0 plus N sub 6 equal to 1. Okay? So, of course, using the same binomial distribution, you should be able to get the answer. Let me just give you my answer from the previous computation. That is 0.466. But be sure to get the answer, okay, later. Compare it with mine. And let me know if my answer is not correct, okay? Okay, so next question is asking the expected number of sevens or tens obtained in 6 throws of a pair of dice. What is this? This is quite a simple question. It's been asking you the expected number of the binomial distribution. Is that right? What is the expected value of binomial distribution? Does anybody remember?
Summation of pi into xi.
Okay, this is, let's say, n6. That's what you want to know, okay? Expected value of the random variable we just defined, okay? Because n sub 6 follows binomial distribution, right? N sub 6. Yeah, mean value. That's going to be n times p. Is that right? What is n? N is 6. What is p? P was 1/4. 9 over 36. Right? There is a p. So what is this? 3 over 2. Okay? 1.5. That's the answer. Very simple question. Okay? Okay, then what about the third question? Excuse me, let me get some water. You know, we are in the middle of nowhere, middle of desert, I say. So it's very kind of helpful for me to carry a bottle of water. Probably you should do that too. Oh, you want to?
How did you get 1/4?
Which one? Here, 1/4?
Yeah.
That is the 9.
Uh-huh.
Oh, okay. 9 over 36.
Oh,
We got that, right? Because there are 6 different ways to get 7 and 3 different ways to get 10. So total 9 different ways to get either 7 or 10 out of 36, right? Any other questions? Okay. Okay, now let's work on the part C. So what is the expected number of throws of the dice to obtain a 7 or 10? How'd you get it? So we want to know the expected number of what? I'm sorry, could you speak up?
Trial to the first event.
Right. Exactly. Great. So again, last time we considered geometric distribution, right? What is that? Again, if we consider the Bernoulli trial, the single trial, if we have this Bernoulli trial independently over and over, okay? I don't know how many times, maybe 10 times or 100 times, million times, I don't know. Just try to do that, okay, independently over and over. Until what? Until you get the first success, okay? Then the geometric random variable counts the total number of trials required for you to get the first success, okay? So this is it. It's been asking you the expected number of how many throws of the dice required to obtain the success. In this case, if you obtain 7 or 10, it is success, okay? Then looks like we need to use geometric random variable for this case. Is that right? Okay, so let me define the random variable first. T sub 1. What is T sub 1? Again, there is number of throws of a standard pair of dice until the first 7 or 10 obtained. Does that make sense? Okay? Of course, T sub 1, this random variable, follows geometric distribution with parameter P. What's P? It's 1 over 4, right? So it's been asking you the expected value of this random variable. What is this? What is the expected value? How do you get it in the geometric distribution? It is 1 over P. So what is this? It's going to be just 4. Okay? So 4 is our answer. So I would say this question C is it's kind of a little bit advanced question compared to question B. Okay? You need to think a little bit more. Okay? Does that make sense to everyone? Okay? Okay, now let's move on to part 3. Oh. Okay. So in this case, we are going to consider a light bulb. Recently, I changed a couple of light bulbs in my home, in my house. You know, these days, nowadays, there is a pretty good quality of light bulbs. It's a lot more expensive than traditional light bulb. There's also LED, and then they all advertise the lifetime of that light bulb is at least like a couple years, 5 years, or even 10 years. But I really doubt it because many of them, yeah, it's not just a couple of them. Many of them, they just died within a year or so. But it's all the reliability issues. But anyway, let's consider an example. about the light bulb. Okay, so in this example, a light bulb in an apartment entrance fails randomly with an expected lifetime of 50 days. Oh, so this is more. This makes sense to me. Okay, and then it is replaced immediately by the custodian. So that's our assumptions. Once it's failed, we assume that the light bulb will be replaced right away, immediately. Okay, and then we also assume that this light bulb lifetime has an exponential distribution. Okay. Then our first question is, what is the probability that a bulb lasts longer than its expected lifetime? Anyway, while we are reading through the problem description, what information did you get? It does say the expected lifetime is 50 days. Is that right? So that means light bulb fails once every 50 days. Is that right? So from this, we'll say lambda is what? It's 1 over 50. Does that make sense? Because lambda is the mean rate. It's not the mean time. Okay? So in this case, this is the failure rate. Okay? Mean failure rate. So light bulb fails once every 50 days. Does that make sense? So it's per day. Okay? 1 over 50 per day. That's going to be lambda. So we're going to first define the random variable as usual. T sub 1 is the what? Time until the first bulb failed. Okay? Time until the first fail. So occurs. Okay. So this is like a lifetime of the bulb. Okay. Could you say so? So T sub 1 is the lifetime of the first bulb. So this is identical to lifetime of the bulb. Okay? Then of course T sub 1 follows exponential distribution with parameter lambda equal to 1 over 50. Okay? Then how do you get the desired probability? We want to know that the probability that the bulb lasts longer than its expected lifetime. So T sub 1 is what? Longer than its lifetime. So it's greater than lifetime of what? What is the lifetime? 50 days. So it's greater than 50. Okay? So that is E2 minus lambda t, right? Lambda is 1 over 50, t is 50. So I'd write down 1 over 50 times 50. So what is this? E2 minus 1. Okay. What is the value of E? Does anybody remember? That is 2.71828. I remember this just like pi. Okay. So E is a numerical constant, right? That is equal to this value. So does anybody have a calculator? So that give me the answer. What is 1 over 2.71828? 0.3679?
787.
787? Okay. So it is 79, okay? Round off. So that's the answer. So that's the probability that a light bulb lasts longer than its expected lifetime of 50 days, okay? Okay, what about the next question then? If the current bulb was inserted 10 days ago, what is the probability that its lifetime, since it was inserted, will exceed the expected lifetime of 50 days? So what is the desired probability? That is probability given that T1 is greater than what? The current light bulb was inserted 10 days ago. Given that information, you want to know what? Probability that its lifetime will exceed the expected lifetime of 50 days. So we want to know the probability that T1 is greater than its expected lifetime of 50 days, which is 50. That is the desired probability. Is that right? Does that make sense? So in this case, we use very, very important property of the exponential distribution. What is that? Memory list property. Sometimes people say it's Markovian property, right? So because of that memory list property, the exponential distribution does not remember that the current bulb was inserted 10 days ago. Okay? So the desired probability becomes T1 is greater than what? 50 minus 10, which is 40. Okay? Because of memory list property. So what is this? It's going to be E2 minus lambda, which is 1 over 50, times T. T is 40 at the moment. E2 minus 4 over 5. Okay? So what is this value? I'm sorry? 0.44? Okay, thank you. You remember in our first class, I mentioned that if probability x is greater than s plus t, given x is greater than t. The same as probability x is greater than s. For all s and t, both s and t are non-negative. And then this is exactly same as probability x, s plus t, x is greater than t, over probability x is greater than t. Is that right? So this part is same as this. And this part is also same as probability x is s plus t. Because this information is redundant, right? If you look at this. So that can be reduced down to this probability. And then finally, this is going to be same as this, right? So I'm going to rewrite down probability x is greater than s. So this part is same as this times this, right? And I also mentioned that this equation is satisfied if x is exponentially distributed. Okay? So that this part is same as E2 minus lambda s plus t. And then what is this? E2 minus lambda s. And this part is E2 minus lambda t. Okay? So if the random variable follows exponentially, if the random variable follows exponential distribution, then it has memory list property. Okay? Because by definition, if this is satisfied, then the random variable has memory list property. Okay? I just want to recall your memory. Okay? This is what we've already discussed in our first class. Okay, now let's move on to the next question. Okay, so if you were to test 10 of these verbs, what is the probability that more than half will exceed the expected lifetime? So which distribution we need to use to answer this question? Which distribution? Again, going back to the Bernoulli trial, which is single trial, whose outcome will be either success or failure, right? If we have that single trial, maybe n different times, then binomial random variable counts random number of successes within those n different trials. This is it, right? It's been asking you the probability that more than half of time it will exceed its lifetime, expected lifetime, within 10 different verbs, right? So we need to use binomial distribution to answer this question. Looks like, right? So we're gonna define n sub 10. What is that? That is the number of verbs exceeded as expected lifetime of 50 days, right? Among how many verbs? Among the 10 verbs tested. Does that make sense? Okay? And of course, this n sub 10 follows binomial distribution with n p. What is the value of n? 10. What is the value of p? What is a p? What is the probability that the verb will exceed? Like verb will exceed its lifetime? Uh-huh.
0.5. Because failure of successful experiment.
No, you gotta be careful. We already got this probability earlier. Where? No. Here, in part A. We already computed that probability, is that right? In part A, it's been asking you probability that the light bulb lasts longer than its expected lifetime. Is that right? What is that probability? That is 0.3679. So we're going to use that probability back down here. Okay? You got to be careful. What is that probability value? 0.3679. That is from part A, earlier. So this is obviously, I would say, advanced question. Okay? You need to think. So what is the desired probability then? Probability n sub 10 is what? More than half.
It's bigger than or equal to 5.
More than half is just bigger than 5. So equal sign shouldn't be included here because it's more than half. Half is 5, right? So it's greater than 5. That is the desired probability. So that's going to be probability n sub 10 is equal to 6, n sub 10 equal to 7, n sub 10 equal to 8, n sub 10 equal to 9, and then n sub 10 equal to 10. Okay? So let me give you my answer from my previous computation. That is 0.11763. But again, you got to double check with this number, okay, this value, and let me know if this is not correct. So is that all make sense to you so far? Okay? Okay, then let's move on to the last question for today. So this is the last question for today's lecture. So if the custodian has 3 spare verbs, it's been asking you, what is the probability that all 4 of these verbs, including the one currently in use, will not be sufficient for the next 100 days? How do you answer this question? So we need to think about which condition, which circumstances, under which circumstances, all of those 4 light verbs, including the one currently in using now, will not be sufficient for the next 100 days.
Time is okay, right?
Hmm?
Time is okay, right?
Okay.
Formal,
Uh-huh.
yeah.
Okay. So how do you define the random variable? The case. So the key point, I believe, is if the force failure occurs within the next 100 days, then all of these 4 verbs will not be sufficient. Is that true, right? If the force failure occurs within the next 100 days, then we'll be in trouble. Is that right? So, because of this fact, I'd like to define the random variable T sub 4. that is the time until the fourth failure. Okay? Then the desired probability T sub 4 is what? T sub 4 is less than equals 100 days, within 100 days. Does that make sense? So T sub 4 follows what distribution?
Airline distribution.
No?
Airline distribution.
Yeah, that is the Erlang distribution. In that case, you need to use the gamma table, right? So last time, I also mentioned that, actually in our first lecture as well. Most of the time, when you need to use the gamma, the Erlang distribution, most of cases, you can use the Poisson distribution, right? Alternatively. So, n sub 100 is greater than or equal to 4 if you use the Poisson distribution. Okay? So simply this probability saying that the number of failures occurred within 100 days is at least 4 failures. Okay? So this is the original probability, desired probability, but we can always use Poisson distribution to get the same probability values. Okay? So using the Poisson distribution, this is going to be the same as 1 minus p n sub 100 is less than or equal to 3. Is that right? So how'd you get this? It's going to be 1 minus probability n sub 100 equal to 3, n sub 100 equal to 2, n sub 100 equal to 1, plus n sub 100 equal to 0. Okay? So that's going to be 1 minus. Let me just do this just one time. It's going to be what? That's going to be lambda. Lambda is 1 over 50, right? So that's same as, what is that? 0.02. Is that right? So 0.02. 0.02 times total number, which is 100 to the power 3 over 3 factorial times E2 minus lambda, which is 0.02 times 100. Okay? So this is the first term, which is this. Okay? So you got to do the same thing for the other 3 probability. Okay? So that's going to be that. And in my previous computation, I've got 0.1429. But again, let me know if these values are not correct. Okay, so be sure to do this, all of this computation later. Okay. Okay, so this is all for today. And next time I will gonna bring you another set of in-class exercise problems. Okay, so we're gonna practice one more, and then probably after that we're gonna move to the next topic, which is discrete time Markov chain. Okay. Okay. Thank you very much. See you next time.